Welcome to the second part of my presentation with the title Spatial Epidemiology with Open Source GIS. In this talk we will take a look at the emerging infectious diseases and new possibilities to analyze them with open geodata in open source GIS. There is an increasing problem of emerging infectious diseases in the world. In this view, I want to focus on zoonotic diseases, that is, usually vector-borne diseases transmitted by ticks, rodents or mosquitoes. Notably, wildlife and domestic animals are the reservoirs for these diseases. They include all types of agents, bacteria, parasites, viruses and others. Being a major health concern, zoonotic diseases are gaining more and more research interest in many countries. The world map shows a snapshot of disease distribution. It is important to know that a variety of factors are causing the pathogen spread: environmental, cultural and political changes. These maps here show two examples: the Crimean Congo hemorrhagic fever and the Schmallenberg virus, which recently appeared in parts of Europe. The Schmallenberg virus causes in the mild form fever of short duration, reduced milk production in cows, and in the problematic form stillbirth and birth defects in sheep, cattle and goats. So it is an animal disease at this point. It is transmitted by Aedes, that is midges. The Crimean Congo hemorrhagic fever is causing all kinds of blood-related issues in the human body, with 30% fatal diseases, and it is transmitted by the Hilaloma tick bites. At the Fondazione Edmund Mark, we work in different EU projects since the 6th Framework Program. Edenext is one of the projects in the 7th Framework Program that deals with the new emerging infectious diseases for risk assessment in Europe. Disease spread is a specific geographical problem, which requires the use of GIS. As an example from Finland, we are studying the hantavirus spread, which is a hemorrhagic fever with renal syndrome in human. It is affected by climate change, for example milder winters than in the past, less snow and more rain, which leads to rodents taking more refuge in houses in small and man-made shelters, hence leading to an increase of human infection risk. During the winter of 2008 and 2009 there was a peak epidemic record with 3,500 cases of hantavirus for a total population just over 5 million people. Another European project we are involved in is the Euro-West Nile project, which aims at the risk assessment of West Nile fever outbreak in Europe. Since 1999 there were several large waves of West Nile virus in the US, with many fatalities. This virus is increasingly spreading in Europe, so that the European Commission requested an assessment of the situation. The interesting part for my work group is the dependence of the temperature, which I will illustrate later on. We are using open source GIS software, basically the GDAL software, which is an interoperability library, Proj4, that is a reprojection library, and GrassGIS. Important for us is to document these algorithms, which have been published in form of software. We have produced a series of publications in the last 10 years, several book chapters and books, and especially a new article about GrassGIS. Furthermore, online documentation and tutorials are available. It is very important for us to document properly the methods and to work in a transparent way. My work group, the GIS and Remote Sensing Unit at the Foundation Edmund Mark, is specialized in processing massive amounts of geospatial data. Luckily, there are huge amounts of US satellite data freely available. Certainly, there are also European data sources existing, but they are much more difficult to obtain. An interesting sensor is the MODIS, which is flown on the Aqua and Terra satellites. Several products are delivered from this satellite system. About 40 different products are available online. Here two examples. One is the enhanced vegetation index, which can be used to detect vegetation onset and autumn arrival and to see the productivity of the vegetation. Vegetation is an important proxy for different risk assessments. Another topic is the land surface temperature assessment. Here an example from the complex alpine terrain, where we have been developing an updated data set. We do data processing on our GIS computer cluster, which currently has 300 nodes available. The MODIS sensor is of global relevance to public health and also other sectors. The situation is that the MODIS sensor offers 36 channels in the range of optical light, near and thermal infrared. From these aforementioned 40 products are generated. It's a strictly hierarchical system from a spatial point of view, and data delivery is taking place at 250 meter, 501 kilometer pixel resolution. In terms of land surface temperature, the error rate is below 1 Kelvin, which is very precise. There are two MODIS sensors available, one on the Terra satellite, since the beginning of 2000 producing data, with an overpass in the morning and also in the evening time. And the second system is on Aqua satellite, started in 2002, overpassing after lunchtime and after midnight local solar time. At this point we obtain 4 overpasses in 24 hours for the entire globe. Data are available after about 72 hours. We've been focusing on one product, which is the land surface temperature. A series of indicators can be derived. This slide illustrates temperature-related products, which are of great relevance for several disease vectors. The point is that we have 4 maps per day, but those can be aggregated to different proxies. One, for example, is the late frost period analysis, which is relevant for masting of trees, which is then triggering the seed production and also the presence of rodents. Another topic is the growing degree days for the phenological status of plants or mosquitoes, for example. From the time series we can identify hot and cold summers, which deviate from average temperatures, and also look at and autumnal temperature decrease, likewise spring warming gradients, which are relevant for the emergence of tick-borne ticks and mosquitoes. And of course all common indicators like temperature minima, maxima can be derived. To show an example what can be done, here a European map which we have produced. The major problem of optical and thermal remote sensing are clouds. They lead to missing pixels in the satellite maps. In the past few years we have developed an algorithm to reconstruct missing pixels with geostatistics using GrassGIS and related open source GIS software. Here are some examples for reconstructed land surface temperature maps. There are 4 maps per day available at the final resolution of 250 meters, but at continental scale. Here we see one map of entirely for about 14,000 maps, which we have almost completed so far. These are 2 different stages, 2 different dates, and we can also zoom into to see some more detail, and you can see the resolution is 250 meter at this point, delivering high resolution of detail. These land surface temperature maps are a time series of more than 10 years now. When extracting all temperature values in 1 pixel, one obtains a time series which looks as shown in the diagram. Each pixel can be considered hence as a virtual meteorological station for near-surface temperature data. Please note that a single map out of these almost 14,000 maps has 415 million pixels. Looking at some applications An important topic is the spread of the tiger mosquito Aedes albopictus, which is an infectious disease vector. The map shows different diseases transmitted by the vector and also the distribution of the vector itself. It spreads meanwhile in Europe as well. It is known in other areas of the world for long decades. It survives and breeds in small containers using also tires and lucky bamboo plants for breeding sites. In 2007 there have been more than 200 cases of chikungunya fever which has been imported by a traveler and has been spread by Aedes albopictus. This is the first case of notable disease spread of a tropical diseases in a non-tropical area. Why is this relevant for us? Because this vector is temperature dependent, and we have been developing a system to analyze the potential distribution of Aedes albopictus from reconstructed MODIS land surface temperature maps. We used 3 different indicators. One is the egg winter survival, analyzed from the January threshold data. The second one is the adult annual survival from annual threshold maps, and the third one is the mosquito life cycle based on growing degree days with a correction for the autumnal temperature. This has been published in the literature. You can see at the page bottom, slide bottom, the links to the documentation and the publications. From these temperature-based indicators we derive a classification, and this classification is then turned into a potential distribution map. In order to do this processing, the cluster of the Edmund Mark Foundation for GIS has been used. These are some technical data of the system. You must know that it is not necessary, of course, to have a cluster at home, but naturally you can also use desktop PCs and it will just take longer. But we plan to publish our reconstructed data in the near future, and like this there is no need to reprocess these data again. Everything is based on open source GIS and also on the R statistical language, and as a grid engine, and grid engine has been used as queue management. Here some results. The tiger mosquito as of today for a small area in northern Italy for the province of Trentino, using the different indicators we have described before. We see 3 different areas: highly suitable, moderately suitable and unsuitable, and the points in the map are trap data, and you can see there's quite some correspondence, but you can also see that it is a potential distribution map. This map has been published 1 year ago. Meanwhile the spread has been ongoing and more records have been obtained so far. We can also use the obtained results to make prediction of the future. This is the tiger mosquito survival in 2050 based on the IPCC A2 scenario, which is the January temperature, mean temperature plus 1.5 degrees Celsius, and the annual temperature, mean temperature plus 1 degree Celsius. This integrated into a map, and you can see compared to the previous map that there's quite some further spread possible. The GIS and remote sensing unit is working on new methods in remote sensing and disease vector borne modeling. Here some overview of recent publications related to Aedes albopictus, 2 publications, one dedicated to the reconstruction of MODIS land surface temperature data, and a third one about Lyme borreliosis situation in Europe. This has been an illustration of application of US satellite data reconstructed, but there are further public geodata available. A very important data set is the OpenStreetMap dataset as an example for crowd sourcing and crowd mapping. An almost famous example is the big earthquake which happened in Haiti in January 2010. As you can see in this map, The geodata of this area were almost absent when this earthquake happened, but thanks to crowd mapping efforts, which means that many people have been doing online digitizing in web browsers based on satellite data which have been made available, in a few days this map has been obtained. And this is an impressive work and giving an idea about the potential of crowd mapping and crowdsourcing, which means that many people contribute, even with small contributions, to a common goal. It is similar to the open source development, but here in terms of creating new geospatial data. And this happens all over the world, and everything is going into the central OpenStreetMap database, which can then be used for different purposes. So the question is, how can public health agencies benefit from open source GIS? We state that there are powerful GIS and WebGIS systems available which can be used for risk assessment. There are also systems available for mobile data aggregation, even with offline synchronization and so forth. Also to perform surveys easily. There are nice portals available which can be implemented. It is important to say that all relevant data standards are available for easy data exchange, so there's no more barrier between proprietary and open source software. We would say that open source GIS is often ahead because new technology development happens in communities which are pretty much skilled in and interested to develop new standards, and also OGC has been adopting some technologies so far. There are many SDI, spatial data infrastructure implementations available to choose from. It is not needed to rely on a single product, but there are many products available, and hence a study which system could be best offer support for the own problems is possible. There's no vendor lock-in with open source software. There's a large amount of companies providing support, and there's no direct relationship between a product and a vendor, but there's the community-based development. We also say that this community support is ideal for sharing new ideas to foster new development, and also to give support to beginners, of course. Some support example can be obtained online. There's the Aedes training program. You can also find the material online, which gives you some introduction to spatial data analysis with open source GIS. To come to a conclusion, emerging diseases are an emerging theme, and they require, because they are complex, the integrated research strategies because of their dramatic impact on well-being and economy. As an example, we have shown Aedes albopictus, the tiger mosquito, current and potential distribution of disease vectors, which can nowadays be modeled at high resolution. This is relevant to Aedes and related health projects. In the talk we have introduced the new reconstructed daily MODIS land surface temperature, which we'll now exploit for various topics in terms of disease vectors. We are very satisfied with the high accuracy, because we have in the first time ever 4 temporary maps per day available, which has not been available in older satellite-based systems, while obtaining a high spatial resolution of 250 megapixels. We state that there are almost unlimited possibilities with free and open source GIS due to the integration of the different packages, the integration of the different communities under the umbrella of Open Source Geospatial Foundation, OSGeo. The systems have been improved. They are now user-friendly and powerful. And software quality is addressed as well. The peer review of the code is very important, and it is an important factor to deliver future software capabilities in the framework of free and open source GIS. Thank you for your attention.